So you probably know that you can tell quite a bit about a scramble just by looking at the moves. So here in the scramble on the second face, these two numbers are the same and they're adjacent, which means that there is going to be an edge-edge case. If one of them was a 0, then that would mean that there is a center edge case. But did you know there's actually one more that you can pretty obviously tell just by looking at this? Here, these two numbers are the same next to the all, which means that you can actually end the solve without having to align to 12. Now, before I explain that, I'm going to show you something that you might have noticed, but never really looked into. So just now I did a hand scramble just on one side, and I didn't add an all move. What I'm going to find is that if I just solve this, I'm actually going to end the solve without having to align to 12. Now, if I do a hand scramble, and I have like a all +1, that means I'm going to end the solve with an all -1. However, that isn't always the case, and I'm going to show you why. So, when you have a move like this, this turns 4 clocks around the dial. If you have a move like this, it turns 6 clocks. If you have a move like this, it turns 8 clocks. But if you have a move like this, it turns 9 clocks. And then for slash cases, it's it turns 7 clocks. So what that means is these moves don't affect parity. They're even moves, and these moves do. Now, I'm not an expert on cube theory, so I can't exactly explain why that's how it is. That's just how it is. I'm going to coin this term CAP, standing for clock alignment parity, and there are 12 CAP cases. So you have like one for each dial, like going all the way around, and the ALLx used to solve it is just like the opposite. Now there are alternative ALLx that use slash move, but I haven't figured out how you can use that, like how you can calculate it and then use it in a solve. So I'm gonna leave that to you guys. This is gonna be like a very different video to what I normally do because I only discovered this yesterday. It's like very underdeveloped. I think it could go further. Right now I've figured out 2 techniques which you could use. One of which is like reasonable, like you could probably actually do it in a solve within 15 seconds of inspection. But the other one's maybe going a little bit too far. It's maybe a little bit unrealistic. So I'm going to explain how you can do tracing. I'm going to put on screen the equation you use to calculate parity. So here I have an example, and I'm going to put the scramble on screen and in the description as well. How it works is you have the corners, you have the edges, and you have the centers, and then you have the second face edges and center as well. Basically, you start at 12. I like to trace it like this. So this one, that's a +3, so you go 3 across. This one, it's a +2, so you go 2 across. These two are 0, so you don't change. This one, I like to go to the centers next because it goes in the same direction. You go 3, oh wait, no, this one's going back 3, so you go this way. And then now onto the edges. These go in the opposite direction, so I like to think of it as starting here and then you're going to 12. So here, from here going there, that's 3. This one goes back 3. This one's a 6. This one goes back 5. So you end up here, and then you flip to a Y2. And then these go the opposite direction. So this time for the edges, it's going from 12. And then for the center, it's going to 12. So 6, and then that's a 4, and that's a -1, -2, and this one's just 6. So you end up here. And you can tell if you did it correctly by looking at the scramble. So here, what I got for parity is 4, +4. And in the scramble, the all moves were 5 positive and 1 positive. So you can calculate parity just by doing the first all, subtract minus the second all. So 5 minus 1, that's equal to 4. So I got it correct. And how you can use it is, if you get 4, so I started on white, and so if I do a 4 plus on the second side, that's gonna save me having to align at the end. But if I wanted to do it on white, I'd have to do 4 negative. So I'll just show how that works. So I'll just do 4 negative here, and then I'll just do the solve. And you want to make sure that you don't align the first face with an all move. You have to keep 1 pin down. And then there we go. I skipped the 12 alignment at the end. The annoying thing about this technique is that you can't use slash moves, which means that you can't do like diag corner skips. In particular, you can't do the double diag, which is really annoying. But you won't be able to use this very often anyways. You're only meant to use this when there's like very little you can find in the scramble. So I guess that should be alright. Okay, now I'm going to show you the techniques I've found with parity. So after you've traced through and you've gotten parity, for the scramble it's 6. I'm not going to show you the tracing because that's going to take too much time. This first technique is solving parity while aligning the first face. So if the parity for this is 6, the good thing is you don't have to worry about which side you have to do like the inverse of. In this case, I can actually solve this face by ending with an all 6 plus. I can also do the same on this side, but it's not what I would do in my pin order. So here I'll do this, this, and then I'll solve parity while aligning this. You wouldn't have been able to solve parity if you did it from this side, in my pin order at least. You're basically picking a better side to solve from, and then you're solving parity at the same time. So once I finish this side, I'll end the solve without having to align to 12. I've left these scrambles in the description, and I'll leave 2 more after this one for you to like find the solution to. For this one, parity is 4 on black, like tracing from white first. Let's see. Yeah, okay, so if I can solve parity with 4 plus on black, then I can solve it with 4 minus on white. And here, after making this cross, I can align it with 4 minus. So I'll do that, and then I'll end with that solved. And yeah, there are 2 more in the description for you to try to find the solution to. Okay, for this next technique, it's a little bit, like for the first one, I think you could do it, you could like plan everything in inspection, but for this next one, I'm not sure if it's possible. I think it's maybe a little bit too unrealistic, but I'll still show it because I think it's really cool. So with this scramble, parity is 4. Basically what you're trying to do is you're going to do the all alignment at the very start of the solve to see if you can create any corner skips. So if parity is 4, I can sort of like visualize in my head that doing this will make no pairs on this side. But if I do this, I'll get these two. This one won't be preserved because I'll want to do this one, but this one will be. So I'll just position that. Hang on. Yeah, parity's 4, so I'll just do that. This is what the scramble was. Yeah, it was here, so I'll do a next 2 from here. So I'll do -4, and then I'll solve here, and then I'll align with this one down because that'll preserve this pair. And then here I also got this one, so I'll just do that one too. And then I'll finish with the alignment done. And there's another scramble in the description for this one. This one's like a lot harder to do because not only are you gonna like spend probably like at least 7 or 8 seconds trying to trace parity, you're also trying to see if it creates any pairs by doing a move on the other side, which is like probably a bit too hard. But I think it could maybe be done if you practice tracing parity enough. Like I reckon you could probably do it pretty fast if you do like a couple techniques. So like if you have like a pair like this in the scramble, then you can instantly know that you don't have to take any of these into account because they'll end up canceling each other out. If you have like zeros, then you can also you can like ignore them. If you have like 2 6s, you can ignore them. I definitely think that you can get tracing down to maybe 5 seconds. I think that is maybe doable. But then again, like this technique is like, it helps you very little, but I just think it's like incredibly cool. Now you're probably asking, is there a shorter equation to calculating parity? And I don't actually have an answer to that. I want you guys to answer that one for me because I have no idea. There are 14 pieces on the clock. It does take quite a while to trace through all of them. But I think this question is quite interesting because there's like a sort of other question that's related to it, and that's proving or disproving the statement that you can determine the state of a piece based on only other clocks. That is, I think, really interesting because every single piece, every single turn changes the state of at least one more piece, including the center getting changed with every single move. So I think that could be really interesting. I also want to show the process we used to creating the equation. It's actually really cool. We had a bunch of simultaneous equations stemming from each of the individual moves. So we had the state of this corner is equal to the turns done by UR, U, R, and all combined. And basically we had an equation for every single one of those for each piece. And then we basically just used like weird algebra to like try to eliminate the moves to isolate all using only like the state of each piece. The person who actually did that was James McDiarmid, so I'll give credit to him. Yeah, I don't know if there's like a better way to do it because we did it by hand. You could probably do it with matrices and Gaussian elimination, but I'm not like good enough with like that kind of stuff. If you're good with that kind of stuff, please try to like find like a better equation. Yeah, I think that's about it. Thanks for watching. I hope you guys find something cool with this technique.